Hi, so this question is critical connections in a network. So you are given a 2D array connections. So A, B represent a connection between the two servers. And yeah, so it's bidirectional. So 0 can go to 2, 2 can go to 0. So you want to return a critical connection, which can be what, disconnect with the other servers. So this question is actually pretty challenging. And where's my picture? So here's my picture. So yeah, so the critical connection is at this point, right? So you can actually take away 1. So 1 and if you take away 1, like 2 and 0 cannot connect to 3, right? But it has to be a bridge. So it has to be a connection. So it has to be like 1, 3. Alright, so this might be the idea, like how to solve this solution. But let's look about like what's the explanation on this solution. So basically you need to build a graph. So 2 can go to 0, 0 can go to 2, 1 can go to 0, 1 can go to 2, and then 2 can also go to 1, right? And 0 can also go to 1. Now 1 can go to 3, 3 can go to 1. Alright, so this is the connection. Like if you're using a bidirectional, it can be easier. So let's look at it. So 2, for the vertex 2, your neighbor is what? 1 and 0. For the vertex 0, you can go to 1 and 2. Vertex 1, you can go to 0 and 2. And 3. So 3, you can go to 1. So this is a graph. We need to build a graph. Then we need to also build a timestamp. So what is this? So I can actually, make this value. So I'm going to start the time with 1, and then I will just initialize, when I traverse, when I spread out, right? So I'm going to just find out if there's a cycle. I'm going to minimize this timestamp from 2 to 1. So in this cycle, like I will get the minimum value for the for this cycle. So timestamp will be equal to 1 at this position. So if there's a condition when I have when my timestamp, this is 1 and this is 4, right? When my timestamp is actually less than the neighbor, then this is going to be the critical connections. So yeah, so let's look at this. I will use the debug mode later, but let's do this. So let's build my graph. It's going to use a hash map integer and take a list integer. I'm going to call map equal to new hash map. So I'm traversing the connections. So I'm going to say x equal to, a equal to connections dot get at 0, b equal to connections get at 1. So map dot compute if absent a. So if I didn't initialize the value for the map, I need to release. I need to get initialize and add my value into my list. So compute if absent b x new release dot add a. So a to b, b to a, I initialize. So let's also initialize my return value and also my timestamp variable. So result equal to new release. Timestamp is actually equal to new int. The size is going to be n, right? How many you have? You have n vertices, then you have n timestamp. So what you need to do is you want to traverse from 0 to 0, and my time is equal to 1, and I will return result. So let's look at the DFS. Void DFS. So I'm going to say, okay, in parent, no, in time. So I will automatically set my time equal to the timestamp at this current spot. It's going to be current node equal to time. So once I said that I can traverse my neighbor, so it's going to be map.get the current node. So this connection has to be built in over here. So you don't need to say get or default in this case. Just get. You get that, and then just make sure your neighbor does not equal to your parent. If so, you want to ignore. This is how you avoid like the cycle, like irrelevant cycle. All right. So once you have that, then you want to look at your neighbor. Does your neighbor set the timestamp? If not, then it will initially to the initial value is actually equal to 0, right? We're not even initial at this. So if this is 0, you know, we know it's not traversing yet, so we just say DFS. Since we are traversing the neighbor, and then we want to stop at the neighbor starting position, so my current node become the parent, my neighbor become the current node, my time will increment by 1, so I will just basically, you know, starting from here, so this is 1, and I probably have to include this. So I initialize time equal to 1, and then I will expand my, you know, neighbor. So 1 and 2 are the neighbor of 0, right? So I would say, okay, this might be 2, this might be 3, right? I mean, if the list is add in this order. If not, then just 2 and 3. I mean, it does not matter, right? Because I will increment my time. So I will assign my time right after I increment, right? So this will be it, right? So this is how it is. So I know these are the traverse value, but I need to make sure my time stamp at the current position, so it's going to be current node equal to the minimum value between my neighbor and myself. Alright, so once I set that, then look at this. So once I set that, then so this is 1, this is 2, this is 3, right? And this will be 4. So once I, you know, set this value, the mean, right? These two guys become 1, right? Because if my parent, if I start right over here, and my children is right here, right? I mean a neighbor. So this will be 2, and so once I traverse this one, I will say, oh, where's my neighbor? My neighbor is this guy. So this will be 3. So it does not spread out, you know, simultaneously. Like it actually looked like this is 1 and these two values are 3, but just think about, you know, the big picture. You're traversing from here, you traverse your neighbor. If not, you do 1 by 1. So I come over here, I increment my timer, I set my timer, and I traverse my neighbor at this current spot. So at this current spot, my neighbor is this one and this one, and I'm not able to, you know, traverse my parent. So this becomes 3 from this node, right? Then I get update based on my parent, based on my what? My neighbor, right? So if I'm at this spot, if I am at this spot, right? This is the timestamp. My parent is this one, right? My parent is this one. My neighbor is this one, neighbor, right? So I traverse my neighbor. So this become my current node. This become my parent, right? My neighbor is this guy, and H1. So I will update my current node with this one. So this become 1, right? And once this traverse finish, right, you will actually update this one to 1, because your neighbor for 2 is 1, right? Your parent is 0 at this timing, if you still remember. So this whole entire cycle is 1, 1, 1, and this is 4, right? So now we need to actually think about this. Are we using this one, the timestamp at the current node, or are we using a time? Time is actually how we increment one by one, right? And be honest, we need to use the time against the timestamp neighbor. This is because you will get you probably will get some of traversal, if this is 4, and then if there's 5, something like this. Just imagine that you are not finished the cycle yet, but you want to find out like what is a critical connection. So you're using the time instead of timestamp at the current spot. So what I mean is this. So if time is less than the timestamp at the neighbor, you just add into the result. So it's going to be what, the current node with the neighbor. So this will be the solution. So let's just run it and then see what happens. Alright, so let's look about time and space first. So this is space. So space are going to be what, all of V, right? But all of the vertices. You need to store the value into the map and also the timestamp. So all of V for the space. The time is going to be all of this one is what, all of C. This is what, all of every single vertex with the edges. So it's going to be V plus E. So this algorithm is actually called Tarzan. I mean, if you can Google, then you probably find it. Anyway, I mean, just make sure that if you, I was looking at this and I can understand, but this is not how it works. So it actually looks correct, but when I was running this, I have some problems. So yeah, so this should be like a cycle, like at some point. Like we have no idea because the cycle might not be complete once we once we traversing, right? Because it might be so just imagine since this graph is a little bit long, so imagine you have some other nodes and then you have connected something like this, and you are at this position, but you actually take your timestamp at the current node, and this is not being updated because it has to be updated based on from here, right? So you need to traverse all of the value, and then from all of the value you want to compare them, then this will be the last scenario, not inside the for loop, maybe like outside, right? And then you want to just traverse again. But in this case, this will be straightforward. You just keep this one. It should be good. All right, let's look at the time and let's look at the debug mode. So if I want to show you the debug mode, I need to do this and also this, and yeah, let's just using this example. Make sure I get anything correctly. Start. Oh, shit. Give me 1 sec. I want to use this test case. So 0, 1, 1, 2, 2, 0, 1, 3. Let's just look at the graph. 0, 1, 1, 2, 2, 0, 1, 3. So this is a graph, right? So if you don't know, you can draw on a paper, and then you'll see it. All right. So in the beginning, I said my timestamp at index 0 to 1. Traversing my neighbor. My neighbor is what? 1, right? So my parent, me, myself is actually 0. My neighbor is 1, so I traverse. Alright, so now I get 2. My parent become 1. My parent becomes 0. And then my current node is 1. Neighbor is 2, traverse. Alright, my current node is 2. My parent is 1. My neighbor is actually 0. Okay, now I can get update, right? Yeah, I get update. So I update my value at current 2, right? With the neighbor. so it should be 1, like 1 to 1 right here. Alright, and I'm comparing my timestamp, this is 3, my neighbor 0, which is going to be 1, so 3 less than 1, it's not how it works, so we just skip, and here, so we come back, so this is a recursion, back here, so parent equals 0, current node equal to 1, neighbor is 2, right, so I need to update this, right, we update it, then let's keep traversing the neighbor, so my neighbor is 3, so my neighbor is actually not traversed yet, so I use the DFS and this becomes 3. Yeah, it should be 3. 1 plus 1, 2 plus 1, 3. Yeah, it should be 3, not 4. So I was making a mistake. So current node is actually what? This is current node. So 1 neighbor is 3, 1 is 3. So for current node it should be 1. So 1, this is 1. Oh, sorry, this is 2. Sorry, this is 2. We're not looking at the time. We're not looking at the timestamp. We're looking at time. The value we initialize to traverse the DFS, and then we look at the neighbor. Does my time is actually less than this one? If so, this is not in the cycle. If that is in the cycle, we update all of the value, everything together, before we traverse on the next neighbor, right? So go over here, you add it. Maybe I need to pause right here. Yeah. So I traverse my what? Current node equal to 1. No, nothing. Yeah, nothing. 0, nothing. Parent 0, 2. Should have nothing, and then I'll update nothing. Nothing. So I will get back to here. So this is how I finish the traversal. So it's a little bit challenge, and then yeah, the problem, the hardest part is going to be this one. You want to understand why it's using a time instead of timestamp at a current node. So yeah, just think about this, and then if you have question, leave a comment, and I'll see you next time. Bye.